So let's start with the RNN, the recurrent neural network. We mentioned that the recurrent neural network is a way of dealing with time series data. Here on the left, we have a standard non-recurrent network where we have, let's say, an input or a vector of inputs, okay, as input to a network which has a number of nodes and parameters. And then at the top of this network is the single output node that is going to yield the hypothesis for a particular input, right? In a recurrent neural network, we're not doing that much that's different. We are just, again, taking the inputs, passing it into the network, using the network to calculate a function that is our hypothesis. But instead of just doing that, we're going to have the neural network recur on itself by feeding its hidden state into another hidden state at a different time step. This representation is a diagram that you might see in other websites, but it's not very clear, I think, from this architecture exactly where this purple arrow goes to. What does it mean for the output of the neural network to go back to itself? So let's get more specific about that. So here I've drawn out those bubbles that we saw before and tried to put in a neural network that we're familiar with into the picture. So at the bottom, again, we have our x1, a particular input that might have 2 dimensions, okay? And these are being fed into the neural network itself, which is this entire green box here, right? Where the green box illustrates all of the nodes, including the ones for the bias. This includes, finally, the single output activation function that's going to lead to our output, which is the execution of the hypothesis as embodied by the entire neural network and its weights to generate an output for x1, which was our input. So now let's unroll this recurrence that we saw on the last slide where we had an arrow going back to itself. So if we were to illustrate another time step, it would look again like this. We would have a new input x2 coming in as, again, the same 2 dimensions, which would go through this network and finally get a hypothesis out for a second input. The same would be true of x3, a third example that's being propagated through the network to generate an output. Now, what's different about this is in recurrent neural networks, we would say these 3 inputs are correlated with each other. They're time series information that would come together. For example, words in a sentence would form the first word, the second word, and the third word, and the predictions for these would come out at the top. But obviously in natural language, word 1 and word 2, the first 2 words in a sentence, are related to each other. It's not random that the first word comes first, for example, a determiner like the or a, and then x2 being possibly a noun, such as boy, neural network, or NUS, okay? So all of these need to be linked to each other. We need to conserve some information about this hidden state and use it to inform our decisions on the second word. How do we do that? Well, we saw the recurrence on the last slide, but what does it actually mean? It means that the output activations of each node are being fed back into a copy of itself at a second time point. So all of these edges in purple are what is being carried over as the output of one particular neuron and feeding it back as part of the inputs to the same neuron topologically at another time step. In fact, all of the weights in the neural network are shared. So for example, this edge here all have the same weight because it is the same model just being applied 3 different times on 3 different inputs. That would be the standard neural network where 3 different inputs are being passed in to the network to realize 3 different outputs. We're also going to preserve the weights for each of these purple arrows between time steps as well. So for example, this particular purple arrow, which is weighted, it has a theta weight attached to it, would have the exact same weight as this particular arrow. Because again, topologically it's the same, but just at different time steps. In this way, a recurrent neural network seems very complicated because of all of these edges, but all of the edges are merely copies of itself at different time steps. We actually use the same weight across all of the time steps, and therefore jointly optimize all of the time steps so that it can optimize their outputs at each point in time. This we can think of as a form of model constraint. Instead of having all of these edges be different weighted, we enforce them to be the same weight so that we have fewer parameters to tune. Now, sequence problems come in many different forms. On the left here, we have our standard one-to-one neural network, where we have one input generating one output. But we can have different variants in the RNN style. We can give one initial input and have several different outputs. So for example, a possibility there is that we put in a particular image and we want to generate a caption for it. So the caption would be a sequence of words which would be primed by the image. Another possibility is that we have a natural language or time series information and we want to generate a single output. So an example of that is to do sentiment classification. That is, for example, predicting whether a sentence is positive or happy versus negative, unhappy. So this would be our +1 or -1, positive or negative outcome. And here would be the words of the sentence. Word 1, word 2, word 3 as a natural language sentence. Many-to-many architectures have several different versions. There's the one here at the bottom, which we'll start with, which is possibly a representation task where we push one form of input in and expect to get several outputs in time series order. An example of this is neural machine translation, where you have the source language sentence here, which is gradually building up a representation of the entire sentence until this point, right? This is our sentence representation. And then using that sentence representation and passing it through again a series of transformations to create an output target language. Okay, which would extend possibly for many outputs until it gets finally to predict the end of the sentence. For example, a period. So finally, there's this other many-to-many model in which we would have inputs at each particular timestamp, but we'd also want aligned or synchronized output as any one point in time. This could be, for example, some type of stock market prediction algorithm, where each time point could be something about the indicators of the stock that might be time sensitive, for example, the prices of other stocks or indices. And then the output could be a buy or sell decision at a particular time point.